start. So good evening to all of you. I am Anjali Dikshit and welcome to the week 8 of Earthquake Geology, a tool for seismic hazard assessment problem solving session. So for this week problem solving session, the first problem that I have taken is, so this is the question, the dash demarcates the boundary between the Indo-Gangetic plain and the high rising Himalayas. Okay, so here we want to name the fault that demarcates the base of the Himalaya, or the place from where the Himalaya range gets started. So for that we have a 4 fault name, and among them one could be the correct one. So the options are main boundary thrust, Himalayan frontal thrust, main detachment fault and main central thrust. So any one of you try to attempt it, or I'll discuss. Okay, so if you'll see the 2D cross section of the Himalayan, so this is how all the faults looks like. So if we'll start from the left hand side, so this wait, let me start my marker. Okay, so this first fault that we are seeing over here, and remember that all these faults are the thrust fault. So this is the unique feature of the Himalayan range has, that all the fault system are the thrust fault system. And since we have gone up to this week 8, so I hope this, what are the thrust fault, reverse fault and normal fault, all those terminologies are clear to you. So the first fault starting from the left hand side is the main frontal thrust, and this fault system is separating the planar range, that is the Indo-Gangetic plain, and from this, as we know that from the Shivalik range the Himalayan starts. So this is the fault which demarcates the boundary from the planar region, that is the Indo-Gangetic plain, and starting from the Himalayan range that we call as a Shivalik range. But if we move further, because in your exams or in any other exam you might face these kind of problems, so let's understand the other fault system that we have for the Himalayan range. So after that MFT, what we get is the MBT, and what this MBT represent? Main boundary thrust, which is the fault that demarcates the Shivalik range with the lesser Himalayan zone. And if we move further then, or going towards more higher altitude, so the next fault system is the main central thrust, which demarcates the lesser Himalayan zone to the higher Himalayan zone. And if we move further then we'll see the Tibetan zone, so let's not move till there. So we'll understand this part only. So always remember that the first thrust fault that we encounter is the MFT, that is the main frontal thrust, that demarcates the planar region, that is the Indo-Gangetic plain, with the starting of the Himalayas, that is the Shivalik range. After that, the fault that demarcates the Shivalik range with the lesser Himalayan zone, it's the MBT, main boundary thrust, and the MCT. So this is the bifurcation of the Himalayan range as per the thrust faults. Okay. Now moving to the, so if we'll try to answer this question, so what they were asking, that what is the fault which demarcates the boundary between the planar region, Indo-Gangetic plain, and the high rising Himalayas. So that is the first thrust fault that we encounter, which is the, can you tell me the answer from this figure? I think anyone can answer. What is this fault? And one more thing, that MFT and HFT both are the same thing. Yeah, so the fault would be HFT. Okay. Now moving to the next question that we have is, which is a very interesting one. a terminology used to describe the rupture along the thrust or the reverse fault that does not rupture up to the surface. So, it is buried under the uppermost layer of the rock in the crust, or no surface evidence is present. I think we have discussed this part in bits and pieces, but yeah, in the problem like proper question form we haven't discussed. So, today we will discuss it. So, now we have a 4 fault. First is the oblique fault, creep fault, vertical fault and blind fault. So, does anyone know like what? Correct, yeah, blind fault. But let us discuss the remaining fault, because you can also have the question related to these faults as well, and you should know that what are these terms. So, we will discuss each and every option one by one. So, the first is the, let us just wait, things. So, the first we will discuss the creep fault. Okay. So, as this name suggests, what does creep means? Creep means that slow or like very slow movement is there. So, this creep fault means that slow or more or less continuous movement which is occurring along the fault plane due to the ongoing tectonic deformation. And one of the advantage of this creep fault system is that since there is a very slow movement or a slow slip is happening along the fault plane, that is why they generally do not tend to have a large earthquakes, because there the accumulation of strain is not happening. So, that is why creep fault are very safest fault system if we talk in terms of the earthquake. So, you might get a question like this, like what fault has a very less probability to have a earthquake. So, in that question you can say that the creep fault would be the one of the option, because here the movement is very slow and they are continuously creeping. So, that is why their stress not get accumulated, and that is why there are less probability to have a earthquakes. Moving to the other type of fault that we have is the oblique fault. So, what oblique means? So far we have discussed the dip slip fault and the strike slip fault, and oblique fault are the combination of these two fault system. So, if I will try to write that oblique fault means they have a dip slip plus strike slip movement. Now, we know what is the dip slip movement. So, the movement that is happening along the dip, and if we take this figure that I have, so this is my dip direction which I am marking with the red marker. So, and this is my strike direction. So, the expression that I got on the surface. And if you see that there is a movement is happening along the strike, and also it is happening along the dip. So, that is why it is a example of oblique fault. I hope it is clear. So, anybody has any doubt, you can ask right away. Okay, good. So, this is the oblique fault. Moving next, as you know, I believe you all know that blind fault are the fault which has no surface, which has no, I think I have wrote it incorrectly, it should be surface. So, which do not have any surface expression. So, if we will see or if we understand from a simple illustration. So, this first figure is the example of the blind fault, because this fault is terminate over here just before reaching to the surface, which is this fault is terminating way before that. And if we take a normal fault example, where we can see that there is a clear cross cutting relation that we got with the fault plane and the surface. So here we can see the surface expression of this fault, but in this first scenario we don't get any surface expression. So that's why it's a blind fault, and this one is the normal fault, or to be very specific, a reverse fault. So since we were trying to identify or look for the answer for this question, so definitely answer would be the blind fault. But also now I hope you have understood all the terminologies, that what are the oblique fault, creep fault, and the vertical fault. I think it's very straightforward, so that's why I didn't explain it. I hope you all can guess that what could be the scenario in the case of the vertical fault. Now moving ahead, this third question that I have taken, here you will get familiar with other terms that we haven't discussed so far, and these terms are very interesting to know, because here we will see a different kind of deformation scenarios. So the question is, excuse me, the thrust faults get bifurcated when projected towards the surface but gets culminated. So remember these words, here they are saying that it is culminated at a certain depth known as dash, along with a dash which could be an increase or decrease in depth of these faults. So what if we will try to decode this question? So they are trying to say that what could be the name of that structure where the fault is bifurcating from a main fault, and then if we will see that they are culminated or get accumulated at a certain depth, where their depth could be increase or decrease. Okay, so the options that we have is decollement, and this increase and decrease, it's depending upon the depth. So first we'll discuss the structures. So among these options, these structures are decollement, ramp flat structure, imbrication, and domino structure. So these four structures first we need to understand, then only we can answer this question correctly. So if I'll go one by one. So first let's understand what are the ramps and flat structures. So from this illustration you can see that if we'll see the first scenario or the first figure that I am marking with 1. So here we have a flat boundary or the flat rupture, and then there is a ramp which is the inclined one, and again we are getting the flat boundary. Now if I look for the analogy, then I can say that it's a stair kind of structure, where you are getting flat, then a inclined surface, then again you are getting the flat structure. Now what is the beauty of this structure? The beauty of this structure is that, like, if it face the compression kind of or extension kind of scenario, where it has to accumulate the displacement that is happening along the fault. So here this is the inclined surface that we can say that it's a fault. But if you are getting the extra displacement, so rather than slipping along this fault line, what it will do, it try to fold. So here you can see that it is trying to getting fold like this. Okay, so this is how it is accumulating the displacement that is happening along the fault plane. And why it is happening? Due to the tectonic deformation, that could be a extension and the compression. Now the question comes, why it is happening? Like in earlier scenarios we see that there is a normal movement will happening along the fault plane. Now why there is the folding kind of structures are forming? So can anybody guess it, like why, like any wild guess? Yeah, pressure on the both side would be the one option, but here in this scenario, why it is happening is because there is a difference in rock properties. What is the difference in rock properties? Like along this flat plane that we marked, the above the flat plane we are getting the soft rocks, okay, soft rocks, and this below the fault plane or the flat plane we are getting the hard rocks, okay. And now what is the soft rock and hard rocks? Please tell me any example of soft rocks, or are you familiar with this word, what are, like soft rocks? If not, then I'll explain it, no issues. Yes, so these soft rocks are the loosely packed rocks, and these hard rocks are the hard rocks, highly compacted rocks. Example of these soft rocks would be the shale, silt, silt could be example, and then another example could be evaporites. And if I talk about the hard rocks, then all the igneous rock, carbonate, under sedimentary, carbonate, or the limestone could be one of the option. But mainly all the rocks that comes under the igneous category or the metamorphic category would be fall under the hard rocks. So since there is a difference in the properties of the rock along this fault plane, and we know that upon stress, if we apply the stress on the soft rocks, they have a tendency to create a fold rather than creating a fault. I hope you have you know this, because we have already discussed it, that for the soft rock, okay. So for the soft rock scenario, we have a tendency that rock will fold rather than because it doesn't have a brittle nature, it has a ductile nature, and the ductile rock have a tendency to create a fold. And if we are talk about the brittle rocks, so they have a tendency to create a fracture or to fault or to break or rupture. So that's why when the stress comes along this area where we are encountering the soft rocks, so that's why this folding is happening along the soft rocks, and this is how it is accumulating. So this is a system where you can see simultaneously both kind of nature. First is a brittle nature that is happening along this, and where you have a fault, and ductile nature through which you are getting the fold. I hope these things are clear. Is it okay? So if we'll see the basic definition of this ramps and fault structure. So ramp and fault structure are characterized by the thin skinned thrust fault terminology. So here you are seeing that we have a thrust fault. Why it is a thrust fault? Now you answer. Why it's a thrust? First tell me what is the thrust fault? It is a thrust fault or the oblique fault? Yeah. Thrust fault are the faults, like they are comes under the category of the reverse fault, but here the dip angle is less than 30 degree. So these kind of fault we called as a thrust fault. Jasurya, are you there? Okay. So would you like to add something regarding this thrust fault that we are discussing? Correct. So what I was saying, so have you getting any idea that why I am saying that it's a thrust fault system? Like if I talk about this first scenario, this one. How? Can you explain it? Hanging wall is moving down. Are you sure hanging wall is moving down in the thrust fault? Yes, correct. So hanging walls is moving up. Now rather than, since we are talking about the ramp and fault structure, and this above rock is a soft rock, so when hanging wall is moving up, so that's why this is creating a folding structure. Okay, in normal fault what we see, like suppose it's a fault and it's a fault plane, and the hanging wall is here and the foot wall is over here. So this is the scenario for the thrust fault or the reverse fault. But here now rather than going directly up, this hanging wall is creating a folding kind of structure. Why it is creating? Because this overlying rock is a soft rock which have a tendency to create a fold rather than creating a like fault. So that's why this fault is not propagating in the up direction like this. So it is creating a folding like of structure because there is a contrast between the rock property along this flat plane. Is it clear to you, or shall I explain it more? Okay. Okay, let me try another way. First, let me clear this. So, okay, tell me that what happens in a normal fault scenario, like if we have a reverse fault, what happens? That in general scenario, like if you have a reverse fault, so then this hanging wall, which is this, will move up, correct? So the movement would be like this, it will move up and this foot wall will move down, correct? This is what we have learned so far. Now what is happening, like what is different in this case that we are discussing is that here we have a different rock properties. What different rock properties? Like along this fault plane, which is a flat plane, above that we have a soft rocks which cannot break because they have a tendency to have ductile. They have a ductile nature. So they have a tendency to create folding. That is a favorable scenario in terms of soft rocks. Earlier what we have a common rock, so that's why, and the rock nature was a brittle nature, so that's why it is breaking, and due to this breaking this fault along the fault plane, this hanging wall move upward and the foot wall move down. But in contrast to that situation, now we have a soft rock above the flat plane and the hard rock below the flat plane. Now if we are in the hard rock zone, like if let's focus, we have here, so there we are getting the normal fault that we are getting in general scenario. Okay, what is different now? Rather now this hanging wall has to move up, correct, and that should be along the fault plane. But since above this flat plane this fault cannot propagate, why it is not getting propagate? Because they have a soft rocks where fault cannot propagate. Yeah, So now there is a displacement that the system has to accumulate and it has to bring it into the equilibrium state. So how now it will accumulate that extra displacement? By creating a folding. Are you getting it? So by creating this folding structure like this, it is accumulating the extra displacement that has happened due to the tectonic deformation. So is it clear to all of you? Any doubt you can ask, it's no issues. That's why we are conducting this session, right? So okay. Moving to the next structure that we have, it's the imbrication. So this is also kind of inlining with the ramp flat structure, but here rather than having a single fault, we have a multiple fault, and these faults are the thrust faults. Why the thrust fault are forming? Because here the scenario is the tectonic setting is the compressional setting, and whenever there is a compressional setting, we will see the reverse fault, right? Right, or anybody has any doubt, then I can explain it, that why in the compressional scenario we get the reverse fault and in the extensional scenario we see the normal fault. Okay. So since it is a compressional scenario, and that you can see that this arrow is also indicating that there is a compression is happening. Now due to that compression, and what is the restriction over here, that it can't go, like here it is restricted, the movement is restricted along this straight line. Now what will happen, like imagine, like, or you can imagine this kind of scenario using the sandbox model, like if the one side is restricted and you are pressing something from the other side and which has a ductile nature, or the both kind of nature, ductile and the brittle. That's why you are seeing the faulting and the folding structure together. So what will happen if we will increase the amount of stress from this direction, so it will try to buckle down, but also the fault will start to creating, and along that fault, since there is an extra displacement that the system has to accumulate, so it try to fold as well, like this. And this kind of structure that we called as a imbrication or the imbrication fan. So if we see the definition of it, it states that an imbricate structure consists of a series of overlapping rock slices. So these rock slices, you can imagine it as like one rock slice, other rock slice, and the third rock slice. So this is the overlapping rock slice. Like over here you have a single rock slice, and for in the case of the imbrication you will have a multiple rock slice, and along this rock slice and these rock slices are separated by a steeply inclined subparallel reverse fault. So since it's a compressional scenario, reverse fault are forming, and they are very steep reverse fault that from this dip you can calculate, like they are very steeply inclined, or the dip angle would be very high, and they are bounded by the major low angle thrust fault surface. So like if you will see at the bottom, you are seeing that there is one black arrow which are indicating the direction. So this is the very low line, like very, like even you can't see that there is any dip angle or not. So that's why it is saying that it's a very low lying thrust surface. and since it's a low lying, so that's why we are calling it as a thrust surface. So if we'll try to compare between, or like to remember to not get confused between the ramp flat or the imbrication kind of structure, I think it's pretty much differentiable. Like here the scenario is completely different. You are a flat, you will see the staircase kind of structure. Just remember it, that in terms of ramp and flat structure, you will see the stair. Whenever you can draw the staircase kind of structure, then definitely it's a ramp and flat structure. But in case of imbrication, there would be a series of sub-parallel reverse fault, and also along this fault you will see the rock slides are piling over. Okay, and it also sometimes called imbrication or imbrication fan, because there are multiple rock slides are forming, so it's a kind of fan, kind of like hand fan kind of shape. So that is the thing. I hope these both structures are clear to all of you. Okay, moving ahead, this dominoes is a very interesting kind of structure, and I think it's the simpler one. After these two complicated structure, now we have a little bit simpler structure. Have you seen these dominoes? Like it's a very like a famous game. So this is the dominoes game where you create a structure, and like for the gaming purpose, or play like for children, and even adults also play. So these are the dominoes. You can see that there's a rectangular blocks, and these numbers are written over here just like a dice, but it has a different shape. So this is a domino. So from there this terminology comes into the geology. But now if we talk about, if we'll try to take this inference and put it into the scenario of the geological case. So suppose here in this first case, this is the normal fault looks like, correct? This is what we have seen. Like if you have a series of fault, so this is how it will look like, or it should look like. So these are the layers. So this one fault, two fault, like these are the parallel faults. But in case of dominoes structure, what will happen? It will have a slip movement also. So you can see that now this whole structure is tilted, and it is tilted like this. It is creating this kind of structure as well. Apart from the faults that are present over here, it is creating this slip over kind of structure. And if you try to take inference from this, the dominoes, the real dominoes from where we took this analogy, like if you try to push, like after putting them into a into any shape, and if you try to push one block, then definitely all the block will fall like this, the same scenario that we are seeing over here, correct? I hope it's easy to imagine, like why we are saying them to dominoes. So the similar kind of phenomena. So whenever there is a large amount of extension, and yeah, one more important thing, like here these dominoes will form in the normal faulting scenario. Now one may ask, like why they are forming in the normal faulting scenario. So the answer to that question, or why the normal, like why this normal fault are not creating, how like अचानक से ये dominoes कहाँ से आ गया है? So one might ask this kind of question. So the answer to that is, whenever there is a high extensional energy, or the amount of extension is high, so definitely it's a extension, the normal faulting would be there. This is the like normal trend. But if the extension is pretty much high, so what will happen? There would be a space between the blocks because extension energy is high. So to fill that extra space, these blocks try to tilt so that they can cover up the extra space in between them. So that's why these dominoes are happening. I hope you are getting it, why they are tilting, because they are getting the extra space. See, always remember, whenever you see any kind of system, every system has a tendency to bring it to the equilibrium stage or equilibrium state. So here, since there is an extra space and this doesn't look like the stable system, so to fill that extra space, that is happening between two blocks. And why there is an extra space? Because the extensional energy is so much high. So to fill that extra space, they tilt to cover up that state, to cover up that space and bring it to the equilibrium stage. Is it confusing? Clear? Okay. I think from this real example, like this is the image of a real domino structure. Now you can say that, like, if you see the normal fault, now okay, tell me honestly, if you see a normal fault and this is also a normal fault, would you can see the difference? Because in the normal fault you not see this kind of tilting, like here it's a tilting kind of feature, but in normal scenario you will see the straight movement. So this is the dominoes. Like if you try to plot it, the hanging football, and then try to see the movement, so this would be my hanging wall which is moving down, and this side is my football which is moving up. So that's a normal fault. And if you see this part of the fault, here also there is another fault. So what is happening over here is that this hanging wall is this hanging wall is moving down and this foot wall is moving up, and this whole system is tilted like this. So rather than a straight inclined line, you are seeing a tilted line. See, all these are tilted in this direction. So that's it's bit difficult to distinguish between the normal fault and the dominoes, but if you will get this extra information that there is a extra extensional energy is playing role in the system, so that is the one keyword. And the another keyword is try to look this kind of feature, like where you will see this ramp up type of feature between the hanging and the foot wall, then you can distinguish. So these are the dominoes. Now moving to the last deformational setting, that is the décollement, which is a French word which means that to detach from. Okay, this is a very interesting one, I can say. So what happens, this is the main fault, the red one, okay. So this would be my main fault or the basement fault. Now from this main thrust fault, and it's a thrust fault system, remember. So from this main thrust fault, all these subsidiary faults are forming. You can see these all like secondary thrust faults are originating from this main fault. So that is the major distinguish of, or the major feature of this décollement. So from this major thrust fault, all the subsidiary thrust faults are forming, and the best example of this décollement is the Himalayan system. And this figure I have taken from the course slide only. From this also you can see the same feature, that this is the main fault which is marking with the red, and all these secondary faults are originating from this main fault. And also remember one other feature is that the lithology or the rock property below this main fault would be more hard rocks or the less deformed rocks, and it could be the igneous rock or the metamorphic rock. And if you see above this main fault, you will see the soft rocks or the sedimentary rocks, which would be more deformed one. And that is why all this deformation or the mountainous range that you can see, it is the sedimentary rocks, and they are more deformed as compared to the basement rock, because they are basement rock or the hard rocks. So, these two are the major features of the décollement. I hope it is clear that the below this major fault, the rock nature would be hard rock, and that is why there would be less deformed rocks, and above this main fault there would be more deformed rocks, and the nature of these rocks would be soft in nature, or they would be mainly sedimentary rocks. And all these other thrust fault system would be originating from this main fault. So, this whole scenario, if I talk about in terms of Himalayan system, is a compressional scenario. Compressional setting, and since it is a compressional setting, that is why we are seeing the thrust fault. So many thrust faults. We have already discussed that this main boundary thrust, MCT thrust, or the Himalayan frontal thrust. So, they all are the thrust faults, and this major fault is also a thrust fault, and that is the similar thing is with the décollement. Here also we have this star is indicating that this rock lithology is hard rock, and here this above part of the rock is the soft rocks, and all these small thrust faults that we are seeing over here, if we talk about the Himalayas, which are originating from this main boundary basement fault or the main thrust fault. I hope this is a very important topic and it is clear to all of you. If not, you can ask it right away. So, this décollement is clear? Yeah. Folding, okay, you are saying this, yeah, this is not exactly a folding, yeah, it is a fault line, but yeah, this is a main detachment fault. Detachment fault or the basement fault, both are the same thing, but yeah, it is a detachment fault, because from this because what is it detaching? It is detaching two kind of lithologies, right? So, that is why it is a detachment fault and the basement fault, and from this detachment fault all the subsidiary thrust fault are forming, that we can see on the surface, correct? Okay. And the major example of this décollement system or the décollement system is the Himalayan fault system that we have. Okay. So, yes, this is okay. Like if like before ending, if we will see the definition of this décollement. So, it is a gliding plane between two rock masses, which also known as the basal detachment fault or the basement fault. So, deformational structure resulting in independent deformation in the rocks above and below the fault, and it is associated with both compressional setting and the extensional setting. So, if it would be in the extensional setting, there would be a normal fault, then there would be no thrust faults, correct? Since it is an example that where it is showing the compressional setting, that is where these thrust faults are forming. But if we will take the example of the extensional setting, then in place of thrust fault, the normal fault will happen, but the overall look of the scenario would be like this only. Clear? Okay. And Himalaya is formed in which kind of setting? Sorry? Your voice is little breaking. Are you saying compressional setting? Yeah, it's a compressional setting. So always, because this related to Himalaya, you will face lots of questions, or even if you go in interview also. So this is a very hot topic. So always remember that about the Himalayan geology. So it is the example of the compressional setting where you all see kind of, that's why you are a system of thrust faults. Okay, so this is from my end. If you have any doubt related to any slide, you can ask me. If you want to me go through all the slides that I have presented, so this is. So I think, sorry, we haven't answered the question that we were trying to discuss. I think somehow we lost in the topic. So can anybody try to attempt to give the answer of this question that we have discussed? I think it's very exhaustive as well, but anyone? And there is no issue if you are giving a wrong answer, then it's another opportunity to learn more. So yeah, feel free to take an attempt. Okay, before attempting, I hope you have understood the question, like what they are trying to look for. Yes. They are culminated, because culminated means they are then converging to a single fault, and like before that they are bifurcating, or they are originating from somewhere. Okay, why do you think it would be decollement? Correct. Yes, because at the end it is getting flat, because this main will go, so this main detachment fault. So if you will see that dip is getting decreases with depth. So here in this direction the depth is increasing. In left side, yeah, what you are saying in left side? Yeah. How dip is increasing? Like if I'll, but if you will see from the as compared to the top, it is continuously decreasing, correct? Like if we will see at this point and try to make calculate the dip, definitely this angle is greater as compared to this angle. So how you can say that it's increasing? I think I didn't answer the question well. You are okay. Why it is okay? How the angle is decreasing? Okay. No issues. Okay, you are focusing on this particular fault, this first fault, like this one, correct? So this one you are talking about. And what's your doubt now? Tell me what's your doubt. Towards the left side. No, but okay, like if first thing, if we let's just focus to the decollement. So here I don't think the angle is decreasing, angle is increasing because the fault are converging to the main detachment fault. This is the first thing, and it's this left side and right side doesn't make any difference, because here what they are asking that like at certain depth known as dash, the dip of these faults are decreasing or increasing. Okay, and if you see just a dip direction, not the left side or the right side, so suppose this is the main fault, and at this depth if I calculate the dip, so it would be some alpha, and at this depth, particular this depth, if I will try to calculate the angle, it would be some beta, and from the visual inspection it is quite clear that alpha is greater than beta. So I don't know why you are saying that dip is increasing. I think you are talking about some other thing. No, we are calculating the dip of that particular fault. So every fault, if you see every fault, the dip is decreasing with respect to depth, and they are at the end converging with the main detachment fault. You understood? Okay, but yeah, you answered correctly that this answer would be the decollement, and the dip is decreasing with respect to depth, and it should be, because at the end they are culminating, because they are converging, and if they are converging, then dip would be decrease or should decrease. Any other doubts? Okay. So Akshay, I think you were facing some you are like confused related to this question, or it's clear now? Okay, good. So okay, you were you were confused between ram flat structure and decollement. But always remember, like in case of ramp flat structure, you will see a staircase kind of feature. So if it is not there, then it's not a ram flat structure. Simple, yeah. Don't get confused. Like whenever confused, try to relate it with a simple things. Okay, for ram flat, related with a staircase. For domino structure, related with this game, like normal game, yeah, dominoes. Like if you press one, then all will fall back, and how they'll fall back, you can imagine that image, and if you are finding in anywhere like here, then it's a dominoes. If not, then it's not a dominoes. And this decollement is a like important one, so remember this thing. So it can happen in the both kind of scenario, compressional and extensional, but this dominoes will always happen in the normal faulting scenario, and this imbrication will happen in the compressional kind of scenario. So these are main key features that you should remember, because these can be asked in any exams. So I think I am done. If you have any doubt, then go ahead, then if not, then we can close the session for this week. So Jasura and Akshay, everything is clear? Okay. Okay, so hope to see you in the next session. I think now there are only 4 sessions are left before you will have the exam. Sorry, after that you will have the exam. So, have you